Liquid C of relative density 0.8 rests on liquid D of relative density 1.2 without mixing. A solid object of density ρ floats with part of its volume in liquid D and the remainder in liquid C. The fraction of the volume of the object immersed in liquid D is ρ minus 2a divided by a. Find the value of a. The relative density of liquid C is 0.8, so to get the density we multiply 0.8 by the density of water, 1000, to get 800. We do the same for liquid D, 1.2 times 1000 is 1200. The density of the object is ρ. Let's look at the forces acting on this object. Well, we have the weight of the object which acts vertically down. So the weight of the object is its mass times g. What is its mass? Well, its mass is its density times its volume v. Now, we can divide this object into two sections. One section has volume vc. That's this section here. That's the part of the object that's in liquid C. And the other part of the object has volume vd. That's the part of the object that's in liquid D. So we can write the volume of the object as Vc plus Vd. Now the object is in equilibrium, its acceleration is 0, so by Newton's second law the resultant force on it is 0. So there are obviously other forces acting on it, of course. We've forces on this object due to the liquids. We have a force on the lower part of the object due to liquid D. So we have to have forces acting upwards to counteract the weight. Okay, this force is called the buoyancy force D. Now this is the force that would be on this shape here if it was just made out of liquid D. Okay, if we can imagine the lower part of the object vanishing and being instantly replaced by the same liquid as liquid D, then the force acting on that liquid would be the same as the force acting on the object. But if this was made out of liquid, the force acting on the liquid would be the same as the weight of this liquid below this line here, if this was made out of liquid. And what's the weight of this liquid? Well, it's the volume of the liquid, it's the density of the liquid times the volume of the liquid times g. Okay, it's the mass of the liquid times g. That's if the lower part was made out of the liquid. Now this is just something we've covered before actually. This is what I'm talking about now was used to prove Archimedes' principle. But I think it's worth restating here because things are a little bit more subtle for the part of the object that's above this line, because it looks like the force on the top part of the object is entirely downwards. Now let's look at the top part. We have a buoyancy force acting up. This is not as clear. It's not as clear that the buoyancy force on the top part acts up compared to the buoyancy force on the bottom part. But let's see how to get this. So this is the buoyancy force on the top part. We'll call this BC, the buoyancy force due to liquid C. Well, again, we can imagine that the top part of the object has been replaced with liquid C. So liquid C here, this new object made out of liquid C, would have the same shape and size as the object that it's replacing, but it's being held here in equilibrium. It's not accelerating. So there must be a force acting upwards on it to counteract its weight, which is downwards. What's its weight? Well, its weight is its mass times g. And what's its mass? Well, it's the density of the liquid, the density of C, times the volume of this region here in liquid C, times g. So now you can see that there must be an upwards force on the top part of the object, okay, to counteract its weight if it was made of liquid, you know. That's a little bit subtle because it looks like the force on the top part due to liquid C is downwards. See, at every point we have a force vector with a downward vertical component. Okay, to sum up, we have used Archimedes' principle on both parts of this object. The buoyancy force in each part of the object is the weight of liquid displaced by the object. And to get the weight of the liquid displaced, we need the mass of the liquid displaced, and the mass is the density of the liquid displaced times the volume of the liquid displaced. Okay, so this object is in equilibrium. A is 0, its acceleration. So the resultant force on it is 0 by Newton's second law. So the sum of the upward components equals the sum of the downward components. There's only one downward component, W, and that must equal the sum of the upward components, BD and BC. We can divide everything by G here. Now we are interested in the fraction of the volume of the object immersed in D. Okay, so that means that we have to take the volume of the object that's immersed in D, which is VD, and divide it by the total volume, which is VC plus VD. Okay, that's how we get the fraction of the object that's immersed in liquid D. So what we will do is we will get either VC in terms of VD or VD in terms of VC and plug into this thing here. I'm going to get VD in terms of VC, so we've rho times VD on the left hand side, and we'll bring over the 1200 VD on the right hand side. I'll shift everything involving VC to the right hand side. So we have rho VC here, I'll shift that over. We have 800 VC on the right hand side, and when we bring rho VC over, we get minus rho VC. Okay, so we brought the VD terms onto the left hand side, and now we can get VD in terms of VC. Okay, if I factorize VC out of the right hand side, get 800 minus rho times VC, and we divide by rho minus 1200 from the left hand side when we do the factorizing on the left hand side. Okay, this is the fraction that we're interested in, so we plug this thing onto the top. So that's 800 minus rho times VC divided by rho minus 1200, and underneath we have VC plus this thing. So luckily here VD is just a number multiplied by VC. That number depends on rho, the density of the object, but because VD has this form, we can cancel VC above and below. Okay, so when we divide below by VC, we get a 1 here. VC divided by VC is 1, and when we divide this by VC, we get 800 minus rho over rho minus 1200. So let's get a common denominator for what's underneath in this fraction. Okay, so we're going to get rho minus 1200 here, because rho minus 1200 divided by rho minus 1200 is 1. And then we're going to get what's left here, 800 minus rho. Okay, so I got a common denominator of rho minus 1200 here. Okay, 1 is the same as rho minus 1200 divided by itself. So rho minus 1200 divided by rho minus 1200 gives us this 1. Alright, notice that the fraction above and the fraction below have the same denominator, namely rho minus 1200. So we can multiply above and below by rho minus 1200 to cancel it out. So we're left with 800 minus rho on top, and underneath we have we see that the rho's actually cancel, and we have minus 1200 plus 800, which is minus 400. Now we multiply above and below by minus 1, and that will give us the result. Well, the result will have this form, as you'll see in a second. Okay, we get plus 400 underneath, and when we multiply 800 minus rho by minus 1, we get minus 800 plus rho, which is rho minus 800. So our answer is, for this fraction, the ratio of the volume of the part of the object in liquid D compared to the total volume is meant to have the form rho minus 2a divided by a, and indeed it does. see, if we let A equal 400, you can clearly see that the denominator is A and the numerator is rho minus 2A. 800 is twice 400. As an aside, notice that the density of the object must be greater than 800 kilograms per cubic meter. That comes out of this formula here. Well, we can say greater than or equal to 800, because, you know, if rho is equal to 800, well, we get 800 minus 800, that's 0. So this fraction will be 0. Vd over Vc plus Vd will equal 0. And if a fraction is 0, it means the numerator, the thing on top, must be 0. So what does this tell us if rho is 800? Well, the part of the object immersed in liquid D will be 0. So none of the object will be in liquid D if the density of this is 0. Okay, I'll just briefly show it here. So if the density is of the object is equal to the density of the liquid on top, then the object will be entirely inside the liquid on top. None of the object will be in liquid D. And that makes sense, because if the density of the floating object is equal to the density of the surrounding liquid, the object will just float in that liquid. Okay, so if the density of floating object and surrounding liquid are the same, the object floats in that liquid. So Vd will be 0. Now, this makes sense because we could just replace the object with the surrounding liquid. And we know that if we did that, this object made out of the surrounding liquid now would just sit here. It would be in equilibrium. The resultant force would be 0. We can do that because the mass will be the same. Whether we use the object with a density of 800 or whether we replace it with liquid D, which is a density of 800, the mass will be the same in both cases. That means the weight mg will be the same in both cases, and if this is made out of liquid D, of course the buoyancy force will equal the weight. So that explains why an object with the same density as the surrounding liquid will float in that liquid.